Hello and welcome to my poster, where I will discuss how one can average the Navier-Stokes equations to obtain Darcy-like equations or lubrication-type equations, but for situations where the viscosity is not constant but is variable and a function of space and time. I'm at the Chemical Engineering Department at IIT Bombay, and this work has been done in collaboration with Dipin Pillai at IIT Kanpur and Ranganarayanan from the University of Florida. So we encounter a wide range of situations in nature and industry where the fluid occupies the configuration of a thin film or flows in a thin gap, where essentially the transverse thickness of the film is much less than the typical scale of variations in the lateral direction. And a bunch of examples are shown here, both for free surface flows as well as for flows in channels and Hele-Shaw configurations, strikingly including the kind of magma flow I will be discussing today. So a central aspect to modeling these phenomena is to essentially assume that the velocity profile has a transverse profile that is in some sense decoupled from the time scale and x variations. And one essentially solves a local problem of the following form, where you see that the y variation of the velocity is related to the local flow rate, and a is a constant that depends on the geometry. Here mu is a constant, so if you solve this you will get simply a parabolic profile, but which is locally adjusted to match the required local flow rate, and dependence on x and time is only indirectly through the variations of the flow rate. However, such an expression makes sense only if mu is a constant. If it is not, then you have the following expression, which is first of all nonlinear, because mu in turn depends on y, right? And that would lead to a non-parabolic velocity profile. But this is a physical feature that is neglected by almost all work on thin films or thin gap flows. And this is despite the fact that there are many situations where viscosity can be variable, either because of its dependence on concentration, as in suspensions, or temperature, as in the magma case I'm going to discuss next. So here you see that you have a situation typically encountered in places like Hawaii, where you have a hot magma rising up from deep within the earth to a crack in the crust. And what has been observed is that initially you have a uniform upflow in the form of a fire curtain, but that you then see a spontaneous transition after a few hours to a kind of channeling where you see a bunch of chimneys. And this is a spontaneous transition indicative of instability. And the question is, what is the mechanism? So a model to study this was introduced by Helfrich as well as Wiley and Lister, where you treat it like a Hele-Shaw flow of a fluid with a temperature dependent viscosity, more specifically a viscosity that decreases as the temperature increases. And it's a simple model for magma. Now importantly, when the hot fluid enters, it meets the cold rock, which is the walls of this Hele-Shaw cell, and as a consequence the fluid near the wall gets a higher viscosity than that at the center. You can also see how this could lead to a nonlinear feedback between temperature changes and flow rate changes, and that's actually what causes this kind of channeling. In any case, the main point is the velocity is strongly non-parabolic. So Helfrich in his original article used a kind of ad hoc Darcy model. So basically he took the usual Darcy model you see at the top of the slide and made viscosity a function of temperature in an ad hoc post facto way. Also in the equation for theta, which is the cross gap average temperature, he introduced a heat loss to the walls in an artificial fashion. In contrast, in our work based on the double IBL method of Krishna Ryo Kill, we are able to derive a consistent model to leading order, to first order rather, where you see that it looks like the Darcy model but with these nonlinear functions f and g that close the problem in a consistent way. To show you a demonstration of the results, this shows you the steady state flow rate in the vertical direction versus the applied pressure. And you see that it's multi-valued, a feature of the nonlinearity of this problem. And this is the full 3D calculation in blue. Darcy is the following, which is quite off quantitatively. And here is our prediction, which does far better. And the reason is that if you look at the velocity profile varying across the gap y, the Darcy always assumes a parabola, which is shown in red. The real full model in blue is strongly non-parabolic. The different curves are for different positions. So at the inlet is the most strongly non-parabolic. And our black lines from the R model match very well. If you look at linear instability calculations, again, our blue curve is much closer to the true black curve than the Darcy red curve. So with that, I'll leave you with a couple of nonlinear simulations of our WRBL model. You see a short wave mode is stabilized by in our problem, whereas longer wave modes become unstable and ultimately lead to channels through nonlinear saturation. So with that, I thank you for visiting my poster and invite you to contact me for further information either directly in the next few minutes or online. Thank you.